Hi, well, I'm Stephen Escherba, and I'm here to help you out with a little bit of analysis of changes in the Gibbs energy of a reaction as a function of temperature and pressure. So I'm just imagining we've got some substance X. It might be converting into Y, and I've drawn the thermodynamic surfaces, the Gibbs energy thermodynamic surfaces, as a function of the state variables, temperature and pressure. And we can kind of, if you want to imagine this, X could be the water vapor, for example, and Y could be liquid water. And so X going to Y would be a condensation process. Okay, and just to see how that works here, we can see here that X, that is to say the gas at low temperatures, is not the thermodynamically stable form. The liquid is. The liquid's the most thermodynamically favorable because it's got a lower G. But as we increase the temperature all the way up to T prime here, then now we discover that the gas is the thermodynamically stable form. And you can make similar comments about the pressure dependence. So when you look up delta G of a reaction in the table, tables are usually given at 1 bar and 298 Kelvin, which is what I'm calling P naught and T naught. So that delta G naught of the reaction is this quantity right here, at distance. And how do you calculate that? Well, I would say I would look up delta G naught of formation of Y, and then delta G naught of formation of X, and then the difference between those is delta G naught of the reaction. It pertains to just that particular point in state space. Now, what if you want to find out delta G of reaction at this other pressure, okay, or maybe at this other temperature? Well, formally, the way we'll write that is we'll say this delta G of the reaction at that different pressure or temperature would be the one right here, plus, however, we need to correct for it by going to different temperatures or pressures. So that's delta G of the reaction. So once we've looked this up in the table, the real hard part is delta G naught, delta G. So how do we get that? Well, I've kind of laid it out here as if we were going along an isotherm or an isobar. Now we know the differential equation of state for G, and so along an isotherm, I could say, well, G changes according to V dP. And that would be corresponding to this sort of path in state space. Okay, we're going along an isotherm. Now, because it's an isotherm, that goes away. So the change in delta G would have to be equal to how V dP for Y is changing, and take away how V dP of X is changing. We can do a little Kirchhoff trick here and say that that integral minus that integral is really the integral of delta V, where V is Vy minus Vx. Okay, so that would be delta V that we integrate. And that works out pretty nicely. Lots of times we can make good approximations here, like, for example, if Vx were a vapor, as we kind of talked about here, then we could use the ideal gas law for this. And if Vy were liquid, well, liquids don't change very much. The volume, molar volume, doesn't change very much with pressure, so that would come out of an integral, for example. How about along an isobar? Well, now we're talking about moving from T naught to T prime, something like that. And so if you were going to use the same kind of Kirchhoffian trick, you would say, okay, the change in delta G of the reaction would be equal to this minus integral of delta S. Why the minus? Well, that's that minus there from the differential equation of state. And the delta S there, of course, is S of Y minus S of X. Okay, so you could do that. Now, it turns out that's not a very convenient way to do that calculation. There's a better way of doing it, thought to be more accurate, and it's the Gibbs Helmholtz equation. And I've written the Gibbs Helmholtz equation this way, and it kind of goes like this. The change in delta G of reaction divided by T now. So we're not looking at the change in delta G by itself, we're looking at the change in delta G over T. Okay, well, that's supposed to be equal to, approximately, the enthalpy of the reaction, and that enthalpy of the reaction, of course, is now going to be H of Y minus Hx, okay? The enthalpy of the reaction times this difference right here, 1 over T prime, the new temperature, minus 1 over T naught. Okay, this is looking a little complicated, but here's kind of how it works. I understand delta G reaction over T to really be, equal to the value where we end up here, which is delta G reaction at the new temperature, and subtract away delta G naught over T naught. That's just what this delta means, okay, and that's going to be equal to all that. So let's just think about what you know. You've already looked up delta G naught of the reaction. That's that quantity right there, okay, and you know that the initial temperature is 298, so we got that term covered. We generally know what temperature we want to go to. That will be T prime. This is the part that we don't know, okay, so far we've just got one unknown here on the left, and we're going to say that's equal to this here, and what do we know here? Well, if we look up delta H of the reaction, and we assume it's good, it hasn't changed very much in going from 298 to our new temperature, times 1 over our new temperature minus 1 over 298, then everything on the right-hand side is known. We know that, we just solve for delta G of reaction at the new temperature, and that's the Gibbs Helmholtz equation, the preferred method of finding how, delta G of a reaction at a temperature different from the reference temperature. Okay.